A mechanical wave is any disturbance that travels through a medium, either a solid, liquid, or gas, which causes the particles in that medium to undergo displacements. So we have two main type of waves, transverse and longitudinal. In a transverse wave, the medium is displaced perpendicular to the wave's motion. So if the wave is moving from left to right, the particles in the medium are moving up and down, perpendicular to the wave motion. In a longitudinal wave, the particles move back and forth in the same direction as the wave. So the particles move left and right instead of up and down. And so all these particles in the medium are oscillating around an equilibrium position. In the transverse wave, the equilibrium position would just be a straight line, and the particles are oscillating up and down around that equilibrium line. So the medium that's disturbed by the wave does not actually move. The particles oscillate back and forth, but there is no net movement of the medium itself. So waves only transport energy, not matter. And for these equations with waves, we're going to use v to represent the wave speed, which is the speed at which the disturbance itself travels through the medium, not the speed at which the particles oscillate. We'll have another expression for that later. And so we're mainly going to be looking at sinusoidal waves, which are the simplest type of wave, where all the disturbed particles are oscillating with simple harmonic motion at the same frequency. So instead of just one thing, say an object on a spring undergoing simple harmonic motion, we have many particles undergoing the same harmonic motion at the same time. And so the wavelength in a wave is the distance between two consecutive points that are identical. So we can have the distance between two crests, which are the peaks of a transverse wave, or two troughs, which are the bottom points in a transverse wave. And so in one period of the particle's oscillations, the whole wave travels one wavelength. So the wave speed is the distance over time, or the wavelength over the period. Or since the period is the reciprocal of the frequency, then the wave speed can also be written as the wavelength times the frequency. And so for mechanical waves, the wave speed only depends on the properties of the medium that it's traveling through. It does not depend on the frequency or any other thing such as the amplitude, period, etc. Because if the frequency changes, then the wavelength also changes. For example, let's say the frequency of the wave is increased. Now, if the frequency increases, the wavelength will decrease, and so this product, the wave speed, will remain the same. So the frequency, wavelength, amplitude, and other properties of the wave itself do not affect its speed. Only the properties of the medium can affect its speed. So in a longitudinal wave, the equivalent of a crest and trough is a compression or rarefaction. A compression is where the particles are clumped together, because remember they're moving back and forth from left to right instead of up and down. So there will be areas of high density, which are the compressions, and areas where the particles are more spread out and have low density, which are the rarefactions. So now we're going to look at the mathematical description of these mechanical waves. So if we want to see the displacement from equilibrium of a single particle, we can represent that as a function of two independent variables. First, we have the position with respect to the source, where the source would be at x equals 0, and the time. So we need two variables to describe this function. Since the displacement from equilibrium of a particle will depend both on the time that has passed and its position. So the displacement of the source can be represented by this equation, which we know is just the equation for simple harmonic motion. And so this is the function when x is equal to 0, since that's where the source is. And so all of the particles in the wave have the same motion as the source. Remember, they're all in simple harmonic motion with the same frequency. However, the particles after the source will be delayed for them to go the same motion as the source. So using the wave speed, we can see that it takes a time x over v for the disturbance to travel from 0 to a point x. So the particle at point x will have the same motion as the source of the wave at a time t minus x over v. So this accounts for the fact that the wave takes some time to travel from the source to point x. So we can describe the displacement of any point at a point x using the same equation but replacing the t with t minus x over v. So notice how if x is equal to 0, then this term cancels out, and we just have the original equation for the displacement of the wave source. And then we can rewrite this because the cosine of a negative something is the same thing as cosine of positive the same thing. So if we multiply this inside of the cosine by -1, it will not make a difference. So that allows us to switch these terms and write the wave equation as this. And then we can further rewrite it, since if we distribute this frequency to these terms, f over v will equal 1 over the wavelength, which we get from this equation over here. And the frequency is the same as the reciprocal of the period. So distributing the frequency to these terms, we can rewrite the equation like this. And there's one more form that we can write this equation in. If we define a number k to be called the wave number as 2 pi over the wavelength, then we can rewrite the equation in this form. So again, k is just a number which is 2 pi over the wavelength. And so which form you use depends on the problem. It's just whatever quantities you are given in the problem will determine which form of this equation is more convenient to use. So now let's look at the motions of the particles themselves, not the whole wave. So we just found an equation for the displacement from equilibrium of a single particle in the wave. So from that, if we just differentiate that, we can find the velocity of that particle. Now, since this equation has two independent variables, we have to take the partial derivative, which is basically just taking the derivative with respect to one variable and pretending that the other variable is constant. So if we want to find the velocity, that's the displacement over time. So we take the partial derivative of this expression with respect to t while keeping x constant. So differentiating we get this expression. Now this is what's called the transverse velocity of the particle. It's how fast the particle, each individual particle, is moving up and down around its equilibrium position, not the speed of the wave as a whole. Now we can also find the acceleration of each of these particles moving up and down by just differentiating this velocity expression again with respect to t, while keeping x constant. And then we can also find the partial derivatives with respect to x instead of with respect to t. So those would represent the slope of the particle's path and the curvature or concavity of its path also. And so if we put the second partial derivative with respect to t over the second partial derivative with respect to x, then we get that equals omega squared over k, the wave number squared, which we can find is just equal to the wave speed squared. Now using the definition of the wave number, 1 over 2 pi over the wavelength. So we can rearrange this to find the wave equation. Now, you won't have to do any calculations with this, but it's an important equation because we know that if this equation appears, then it's describing some wave or disturbance traveling through a medium at a speed v.